Good morning, everyone. Welcome to another lecture. In the last lecture, we discussed Venn diagram and what actually it represents. Then we deliberated set operations, mainly the union of sets and its various properties. In continuation with the union of sets, today we will discuss another operation, namely the intersection of sets and the different sets and their different properties. So first we are going to consider the intersection of sets. See, the intersection of sets is an operation that results in a new set which contain only the elements common to both original sets. So this is generally denoted in terms of the symbol. So it is inverted U, that is denoting for the intersection of the sets. If we have two sets, that is say set A and set B, then the intersection of set A and set B denoted as A intersection B, which is defined as A intersection B is equal to, it is the set of all elements of X such that X is the element of A and X is the element of B. We can read it, it is the intersection of set A and B, which is the set of all elements of X such that X belongs to set A and set B. That means A intersection B include all elements that are common both in set A and set B. So if there are no common elements between two sets, then the intersection is empty set, and then we have disjoint set. The given two sets are generally known as it is disjoint sets. That means we have no elements in common, which are generally known as it is mutually exclusive sets. For example, we have given set A is equal to 1, 2, 3, 4 and 5. Set B is equal to 3, 4, 5, 6, 7. Then the intersection, that is A intersection B, would be 3, 4, 5, which are common here, that are the elements common to both sets. So here the common elements are, see, 3, 4, 5, 3, 4, 5. In both sets 3, 4, 5 are there. So we can say that A intersection B is equal to 3, 4, 5. So in this case also, the order of elements in the intersection doesn't matter, and the repetition are also not considered. Each elements are listed only once. Now we are going to represent the intersection of sets by using Venn diagram. See, the Venn diagram for the intersection of sets look like this. See here, as we are already discussed that the Venn diagram, which the sets are represented by using the circles, and the overlapping region between the circles represented the intersection of those sets. So this is the overlapping area, that is this shaded area, which is generally known as it is A intersection B. So here the circle A represents set A and circle B is representing the set B. If we have an overlapping region between circle A and circle B, that means there are some common elements in the given sets, and that are shown in this particular shaded area, that is denoted in terms of A intersection B. So here this shaded area is considered as the A intersection B, and it is enclosed by, we have a rectangle, and this rectangle is nothing but it is the universal set. Now let us consider an example of set A, which is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and set B is equal to 2, 3, 5, 7. We want to find out A intersection B, and we want to show that A intersection B is equal to B. See, the intersection of sets A and B is generally denoted as A intersection B, which is defined as it is the set of all elements that are common in both sets. So accordingly, our answer will be C, A intersection B is equal to, see here, 2, 3, 5, 7, which are common in set A and set B. So accordingly, A intersection B is equal to 2, 3, 5 and 7, which are also equal to set B. So why it is equal to set B? This is because set B is the subset of set A. So we can say that if B is the subset of set A, then A intersection B is equal to B. Here B is considered as the subset of set A, then we can say that A intersection B is equal to B, which we are already proved here. So if B is the subset of A, then the intersection of these sets are equal to set B. This is because every element in set B is already in set A, and the intersection do not add any new elements to set B. So we can say that A intersection B is equal to B when B is the subset of A. Now we are going to discuss various properties of intersection of sets, which are essential for understanding how set interact and how the intersection operations behave. So here we are going to consider the first property, that is commutative law. That is A intersection B, which is equal to B intersection A. That is, the commutative law shows that A intersection B is equal to B intersection A. This particular property proves that the order in which you intersect the sets does not change the result. Whether you intersect set A with set B or set B with set A, you will end up with the same set of common elements. So we can prove the commutative property of set intersection by using an example, that is set A is equal to 1, 2, 3, 4 and set B is equal to 3, 4, 5, 6. Now let us find A intersection B, that is intersection of A and B, that is all elements that are common in both set A and B. So here A intersection B will become, see, it is 3 and 4, which is common in set A and set B. So A intersection B is equal to, it is 3 and 4. Now we are going to apply the commutative property, that is, now we have to find B intersection A. What is B intersection A? So here again it is those elements which are common in the set A and set B. So it will become, see, B intersection A, that is equal to 3 and 4, 3 and 4. So here it is also 3, 4. So we proved here that the order in which you intersect A and B, it does not affect the result. The result is the same set of common element, that is 3, 4, 3, 4 here also, that is A intersection B is equal to 3, 4, B intersection A is also equal to 3, 4. So we can say that the commutative property hold in the case of set intersection. Then the second law associated with the set intersection is associative law, which says that A intersection B intersection C, which is equal to A intersection B intersection C. See, we know that the associative law actually emphasizes that grouping of sets when performing multiple intersection does not affect the results. So whether you first intersect set A and B and then intersect the result with the set C, or if you first intersect B and C and then intersect the result with A, we will end up with the same set of common elements. Let us consider one example of set A, B and C, and we are going to prove the associative law, that is A intersection B intersection C, which is equal to A intersection B intersection C. So we have the given set A is equal to 1, 2, 3, 4, set B is equal to 3, 4, 5, 6 and set C is equal to 4, 5, 6, 7. See, first here we want to find A intersection B intersection C. So here that is the intersection of A and B then with C. So here first we are going to consider A intersection B, so which is equal to 3 and 4. A intersection B, here the common elements are 3, 4, here also we have 3, 4. So we are writing here A intersection B is equal to 3 and 4. Intersection C, what is C? It is 4, 5, 6, 7. So I am writing here it is 4, 5, 6, 7. Now we are going to intersect, that is A intersection B intersection C. So here the common elements are, here it is 4. Here only one element, that is 4. Now we are going to consider the right hand side part, that is A intersection B intersection C. So now here first we are considering A intersection B intersection C. So it is A, that is 1, 2, 3, 4 intersection B intersection C. What is B intersection C? It is 4, 5, 6. 4, 5, 6 are common here in the both set B and set C. So here I am writing it is B intersection C is equal to 4, 5, 6. So A intersection B intersection C is equal to 1, 2, 3, 4 intersection 4, 5, 6, which is equal to 4. So here A intersection B intersection C, which is also equal to 4, then A intersection B intersection C, which are also equal to 4. Hence we can say that the result is the same, that is 4 regardless of the grouping. So the associative law hold, that is A intersection B intersection C, which is also equal to A intersection B intersection C. So we have proved here the associative law of intersection of the sets. Now the another law, that is law of empty sets, that is phi intersection A, which is equal to phi. See, actually this law states that the intersection of empty set, that is phi, with any sets will always the empty set, because no elements can be common between empty set and any other set. For example, see, set A is equal to 1, 2, 3 and we have null set, that is empty set also, that is phi. So if you are going to take the phi intersection A, so why phi intersection A is equal to here? It is phi, because there is no common elements between the empty set and any other set. So this is the law of empty set. Now the another one, that is law of universal set, which says that the universal set intersection A, which is equal to A. This law actually proves that the intersection of the universal set with set A always the set A, because every element of set A is also in the set universal set. So the intersection doesn't add or remove any elements from set A. For example, so that we can say that the universal set intersection A is equal to A. For example, we have a universal set which is equal to 1, 2, 3, 4, 5, 6, 7 and set A is equal to 1, 2, 3. Now we are going to find out universal set intersection set A, that is U intersection A, which is equal to 1, 2, 3, 4, 5, 6, 7 intersection 1, 2, 3. So here the common elements are 1, 2, 3, 1, 2, 3 here. So we can say that the universal set intersection A, which is equal to 1, 2, 3, which proved that the intersection of the universal set with set A is always a set A when A is the subset of the universal set. Now we have another law related with the intersection of set is idempotent law, that is A intersection A, which is equal to A. And this law states that the intersection of any set, for example set A, with itself always reproduce the set A. The operation does not change the set and it remains the same. For example, we have a given set A is equal to 1, 2, 3. Then A intersection A, that is 1, 2, 3 intersection 1, 2, 3. So 1, 2, 3 intersection 1, 2, 3, which is equal to 1, 2, 3. So A intersection A, which is also equal to A. So it can also say that when we have a repeated intersection with the same set has no additional effect. That means A intersection A intersection A intersection A, which is also equal to set A, because applying it multiple times to the same set does not produce any different outcome beyond the first application. So A intersection A, which is also equal to A. Now we have another law, that is distributive law of union and intersection. See, there are two properties associated with the distributive law of union and intersection. The first property is, see, A intersection B union C which is equal to A intersection B union A intersection C. This law actually shows that the distribution of intersection operation over the union operation, that is the intersection of set A with union of set B and C, is equivalent to the union of intersection of A with B and A with C. So we are going to prove this particular law by using an example, that is set A is equal to 1, 2, 3, set B is equal to 2, 3, 4 and set C is equal to 3, 4, 5. Then first we are going to consider A intersection B union C. So what is A, which is equal to 1, 2, 3, intersection B union C. So B union C, here it is 2, 3, 4, 5. 2, 3, 4, 5 will become B union C. So here A intersection B union C, that is 1, 2, 3 intersection 2, 3, 4, 5, which is equal to, what is common here? It is 2, 3. So we can say that it is 2 and 3. Similarly, now here we are going to consider A intersection B union A intersection C. So here what is A? 1, 2, 3 intersection B, which is 2, 3, 4 union A intersection B, that is 1, 2, 3 intersection 3, 4, 5. So if you solve it, then 1, 2, 3 intersection 2, 3, 4, which is equal to, it is 2 and 3, which are common here. Then union 1, 2, 3 intersection 3, 4, 5. So here it is only 3 is common. So we are taking here it is 3. So it is 2, 3 union 3, which is equal to 2 and 3. So here also see A intersection union C, which is equal to 2 and 3. A intersection B union A intersection C, which is also equal to 2 and 3. Hence we are proved here, that is A intersection B union C, which is equal to A intersection B union A intersection C. The second property, which is actually states that similar to the previous property, we have A union B intersection C, which is equal to A union B intersection A union C. So similar to the previous property, we have the another property related to the distributive law of union and intersection. So it is equal to A union B intersection C is equal to A union B intersection A union C. And this law actually states that the distribution of union operation over the intersection operation, and it proved that the union of set A with intersection of B and C is equivalent to the intersection of union A with B and the union A with C. We can prove it by using an example. See here, set A is equal to 1, 2, 3, 4. Set B is equal to 3, 4 and 5 and set C is equal to 4, 5, 6. Now we want to prove that is A union B intersection C is equal to A union B intersection A union C. So we are going to prove it. See, the first one we are going to consider here B intersection C. What is B? 3, 4, 5 intersection C 4, 5, 6. So here the common elements are 4, 5, 4, 5. So I am writing here only 4, 5. B intersection C is equal to 4 and 5. Now we are treating A union B intersection C. So it will become, what is A? 1, 2, 3, 4 union, then B intersection C, which is equal to 4 and 5. So it will become 1, 2, 3, 4, 5. 4 is repeated here, so we are going to consider only once. So it will become, see, A union B intersection is equal to 1, 2, 3, 4 and 5. Similarly, we are going to find A union B intersection A union C. So first here we are considering A union B. So A is equal to 1, 2, 3, 4 union 3, 4, 5, which is equal to 1, 2, 3, 4, 5. Similarly, A union C, which is equal to A 1, 2, 3, 4 union C, which is equal to 4, 5, 6. So we can write A union C, which is equal to 1, 2, 3, 4, 5 and 6. See here, both A union B intersection A union C, which is equal to 1, 2, 3, 4, 5 intersection 1, 2, 3, 4, 5, which is equal to 1, 2, 3, 4, 5. Hence, we can say that A union B intersection C, which is equal to A union B intersection A union C. See, now we are going to consider another set operation, that is difference of sets. See, the difference of sets is an operation that actually results in a new set containing all elements of one set that are not present in another set. So if we have two sets, for example set A and set B, then the set containing all those elements of A which do not belongs to set B is known as the difference of two sets, and generally it is denoted by the symbol that is A minus B, or we can say that A difference B. So mathematically we can write A minus B, which is equal to set of all elements of X such that X is in set A, or X is belongs to set A and X is not belongs to set B. So here A minus B is the set of all elements of X such that X is the element of A but X is the not element of B. So here A minus B include all elements that belongs to set A but does not belongs to set B. So the set difference, that is A minus B, can be represented by using the Venn diagram here. See, which is shown here, that is set A, which is represented by the left circle, and set B is the right circle, and the shaded region or the shaded area is represented as the elements in set A but not in set B. So this area will be considered as the A minus B. Similarly, the set difference can be B minus A, which means that set containing all those elements of B which does not belongs to set A. Mathematically we can write B minus A, which is equal to set of all elements of X such that X is the element of B and X is the not element of A. Or we can say that B minus A is the set of all elements of X such that X is belongs to B and X is not belongs to A. So the set of difference, that is B minus A, by using the Venn diagram we can shown here. See, here the set A is represented by the left circle and set B is the right circle, and the shaded area or the shaded region is represented the element in B but not in set A. So this is the area, this shaded area is considered as the B minus A. For example, we have given set A is equal to 1, 2, 3, 4, 5 and set B is equal to 3, 4, 5, 6. Then the difference, that is A minus B, would be we have to identify those elements in set A that are not in set B. So here A minus B, which is equal to, see, 1, 2, which are in set A but they are not in set B. So here it is 1, 2 is considered as the A minus B. See, regarding the difference of set, there are three important points should be noted here in connection with the difference of the sets. The first one is, see, you should be kept in mind about the difference of set is that the order of sets matter in the difference operation. Unlike the intersection and the union, here the order of the sets matter in the case of a difference operation. That means A minus B is not equal to B minus A, or we can say that A minus B is not the same as B minus A. We can prove it by using an example. We found that A minus B, see here the example of A, B is given here, and A minus B we are already calculated here, it is 1 and 2. Now we are going to calculate B minus A. What is B minus A? It is those elements of X which are in B but not in set A. So B minus A is the set of all elements of X such that X is in set B but not in set A. So accordingly, see 3, 4, 5 which are also in set A, therefore B minus A is only 6. So B minus A represent the element 6 which is in set B but not in set A. Now the second important point should be noted down here, that is if set A and B have no common element, That means A intersection B is equal to a phi set. Then the set difference, that is A minus B, which is the same as set A. Mathematically we can write, if A intersection B is equal to phi, then A minus B, which is equal to A. This is because when A intersection B is phi, that means there are no elements that are common in set A and set B. Then the set difference, that is A minus B, we know we have to remove the elements of B from A, but since there is no common elements, A remain unchanged. Therefore, we can say that A minus B, which is equal to A, if A intersection B is equal to phi. The same way, we can say that in the case of set difference of B minus A, if set A and B is phi, that means A and B have no common elements, then the set difference, that is B minus A, is equal to B. See here, A intersection B, which is equal to phi, that is null set, then B minus A, which is equal to B. This is because B minus A, we are removing the elements of A from B. Since there is no common elements, B remain unchanged, and mathematically we can say that if A intersection B is equal to phi, then B minus A is equal to B. The third most important point you should be kept in mind, that is if A is the subset of B, then A minus B is the empty set. That means if A is the subset of B, that means we can denote here A is the subset of B, then the set difference, that is A minus B, is equal to phi. So when A is the subset of B, then A minus B is equal to phi. This is because if A is the subset of B, it means that all the elements of A are also in set B. When you take away the elements of B from A, then there are no elements left in A that are not in B. So resulting, we will have an empty set. Therefore, we can conclude that A minus B is an empty set when A is the subset of B. Now we are going to consider some of the important properties of different sets. The first one, the complement identity property, which means that A minus A is equal to phi. This property actually states that the difference of set with itself result an empty set. We can prove that is A minus A is equal to phi by using an example, that is set A is equal to 1, 2, 3, 4, 5. Then A minus A, that is 1, 2, 3, 4, 5 minus 1, 2, 3, 4, 5, which is equal to a phi. That means A minus A, which is equal to phi set. When we take the difference of set A with itself, we will remove all the common elements, then we will get an empty set, that is phi, because every element in set A is also in set A. Thereby we can have only an empty set. The second property, that is empty set difference property, which actually states that when we take the difference of any set, say set A with empty set, which result in set itself. That means A minus phi, which is equal to A. This can be proved by using an example, that is set A is equal to 1, 2, 3, 4, 5, and we have a null set, that is phi. Then A minus phi, which is equal to 1, 2, 3, 4, 5 minus 5. That means which is also equal to A. So if you take the A minus phi, which is equal to 1, 2, 3, 4, 5, so it is also equal to the original set, that is set A. So when we take the difference of set A with empty set which have no elements, we basically remove no elements from the set A. Therefore, we can say that A minus phi, which is equal to 1, 2, 3, 4, 5 here, which is also equal to A. Hence, the empty set difference property, the result is set itself, that is A minus phi, which is equal to A. And the last property, we can say that associative property of set difference, that is A minus B minus C, which is equal to A minus B union C. See, this property actually indicates that the order of performing set differences does not affect the result. As long as you are going to subtract the same sets. That means the grouping of sets within the parenthesis does not change the outcome. It can be proved by using an example. Consider the set A is equal to 1, 2, 3, 4, 5, set B is equal to 3, 4, 5, 6 and set C is equal to 5, 6, 7, 8. Now let us evaluate both sides of the associative property, that is A minus B minus C. So what is A minus B? A minus B, here it is 1, 2, 3, 4, 5 minus 3, 4, 5, 6. So it will be only 1 and 2. A minus B is equal to 1 and 2. Then A minus B minus C. What is A minus B? Which is equal to 1 and 2 minus 5, 6, 7, 8, that is C. So which is also equal to 1 and 2. Similarly, here A minus B union C. So A minus B union C, here B union C is equal to B, that is 3, 4, 5, 6. C is equal to 5, 6, 7, 8. So B union C is equal to 3, 4, 5, 6, 7, 8. Without considering the repetition, B union C is equal to 3, 4, 5, 6, 7, 8. Then A minus B union C. What is A minus B union C? That is 1, 2 minus 3, 4, 5, 6, 7. That is also equal to 1 and 2. Therefore, we can say that A minus B minus C, which is also equal to A minus B union C. So these are the various properties of the set difference. Let me conclude here. In this lecture, we have discussed set operations, namely the intersection of sets and the different sets and their properties. I hope you understand all these operations very well. In the next lecture, we will discuss the complement of a set and its various properties. Then we also discuss, De Morgan's laws. So we'll see in the next lecture. Thank you.